All right, let's look at another proof here. Proposition 4. Given a line and a point not on a line, there exists exactly one plane containing the given point in the line. We should be able to prove this directly using our set of postulates that we have so far. You should see that list in the previous video and previous videos. Again, let's try this one yourself before reading on the next page. This one has a few more lines to it, to the proof. I think this is a more interesting one for you. Give it a shot yourself. Press pause now. All right, well, we're back. Let's go and look at the proof. Well, first of all, we have this. Given a line L and a point A such that A is not on L, prove there exists exactly one plane containing L and A. So the start is very basic and given. Automatically, we know that the first statement is there's a line L and a point A such that A is not on L. That's the given hypothesis. That's the reason. Moving down the road down here, we know the last statement is going to be there exists exactly one plane, which we've called P earlier in the proof, containing A and L. All right, so here we go. So we've got to make a chain of statements to pull these together. Notice that the reasons for each statement are earlier statements and postulates. And notice when I'm writing that, I identify the statement and the postulate. Now, if I had my list of postulates right here on the same page, then I might just say postulate 5. But since I don't have my list, I want to actually write what the postulate says here in the reasons. So let's see if we can go through this one. So we started with there exists a line L at a point A such that A is not on L. So now that we have a line, we can use postulate 5. Postulate 5 says every line contains at least 2 points. Notice you must have a line first. So this one basically could be rewritten as saying if L is a line, then there exist points B and C on that line. Okay? Which is exactly what we've said here. But how do we know there is a line? Well, that's in statement 1. So we have to establish the hypothesis of postulate 5 in an earlier statement to be able to use postulate 5 to get the conclusion of postulate 5 as our second conclusion or second statement. So notice that the reason is statement 1 and postulate 5. So now what do we have? So far we've got a point A. It's not on the line L. We got points B and C on the line. So L, the unique line containing B and C, is the only line containing points B and C. Well, let's look at statement 2 and postulate 6. Given any 2 distinct points, where do we get those? Well, from statement 2, right? If B and C are points, then what? There exists exactly one line that contains both of them. So the unique line containing B and C is L. Notice I couldn't call this line BC to begin with because I didn't have the points B and C until I invoked postulate 5 to give them to me. Now, let's look at the points A, B, and C. That's a set of points. I claim that's a set of non-collinear set of points. So let's look at statements 1 and 3. If these points were collinear, then there would be a line containing the 3 of them. However, A is not on line L, and L is the only line containing both B and C. That comes from statements 1 and 3, putting them together. Now that we have a set of 3 noncollinear points, we can use postulate 7. So statement 4 goes with postulate 7 as our next reason. Given any 3 distinct noncollinear points, there exists exactly one plane containing them. So our conclusion is there exists exactly one plane, let's call it P, containing points A, B, and C. All right, so now we have a plane containing A, B, and C. Now L is in the plane P, so P contains A and L. And there exists at least one plane containing A and L. That's my next statement. How did I get that? Well, I had to use postulate 8 and statement 5. So plane P contains points A, B, and C, but postulate 8 says if 2 points lie in a plane, then any line containing them lies in that plane. So, of course, with line L is there. Okay, so I'm actually using statements. Actually, I need statement 3 there as well. Statements really 3, 5, 3 and 5. And postulate 8. Postulate statement 5 satisfies the hypothesis of postulate 8, and then the fact that statement 3 says L is the only line containing them, put that together. So we know that L is a line containing the 2 points. That gives us that. But then statement 6 says if there were another plane that contained A and L, then that would also have to contain points A, B, and C, but that would contradict statement 5. So that gives us finally our final conclusion that there exists exactly one plane containing A and L. Now this is a good proof here because it puts together a string of things. It makes use of postulates 5, 6, 7, and 8. If we only had say any three of them without the fourth one, then there'd be a way to make a geometry where this proposition is actually false. The statement in this proposition. So it's not just any one of these postulates, but the interplay among those four that makes this work. So notice carefully how everything was stated. Okay, looking back, we notice that every step except the last one was used as a part of the justification for a subsequent step. This shows that every step is actually needed and it's documented well. You should always look back at your proof and check to be sure that every step is used somewhere in the reasons column later on. If not, one of two things either happen. You don't really need it in the proof, that's less likely, or you failed to properly and fully document the use of the step later in the proof, that's a more likely mistake. We've been tacitly using postulates 1 and 2 without referencing them. We're going to continue doing that throughout the course. So now we've done a few of these, let's go on to proposition 5 before reading on and see if you can prove that. If two distinct lines intersect, their union lies in exactly one plane. Work that one out for the next, before you watch the next video.